Hi, class. So when we left off last time, we were speaking about images of the universe as taken by the Hubble telescope, and you can see that we can see a number of galaxies out in this one particular view, and pretty much everything that we know about the universe, we know because of the light that we can detect, because of the light and the radiation that we can detect coming in from objects all around the universe. So the fact that how do we know this galaxy exists? Because we can detect it. We can see it. We can see it because the Hubble telescope, which is a very powerful instrument, detects the light coming from this galaxy. So it's important to talk. So that I just wanted to say that as an introduction to what you guys watched in the recent videos, which is light. Okay, so the recent videos that you watched in Khan Academy had to do with light and fundamental forces. So as you were listening to the video, um, you learned several things about light. And you already know that light travels very fast, 3 times 10 to the 8th meters per second. Um, and he was mentioning that light travels as a particle called a photon, Photon, photons. And so light really travels, it is a wave. It behaves like a wave, much like a water wave. So that wave of energy, if you create a disturbance in water, that wave of energy propagates outward. Um, or a sound wave, when you speak, a wave of sound energy propagates from your vocal cords out and kind of spreads out into the room. So waves, in one sense, have a speed. Light waves are very fast. Sound waves are kind of fast as well. Not anywhere near the speed of light, but sound waves are relatively fast and travel across a room fairly quickly. So one thing about light is that they have a very, very fast speed, and the energy in light tends to stay together in little packets, or little what's called photons of energy. These are very, very, very small packets of energy. So it's very difficult to detect individual bundles of energy, but light does travel as individual little chunks of energy called photons. Now, one thing about light, and we often talk about light. And when we talk about light, we normally are referring to visible light, the stuff that we can see. Red light, orange, yellow, green, blue, indigo, violet, what we consider the colors of the spectrum. If you put white light through a prism, you see all of these colors. But early on, well, let's say 150 years ago, when people were doing some experiments, when they could have a piece of glass like a prism made, and you could therefore get these different colors coming out. Certain scientists began to do some experiments, and and this is just a picture of one of those early experiments. So this is a while back, before we had very sophisticated instruments. What's going on here is this particular person put light through a prism and then put thermometers in the different colors, and he was trying to experiment with, do the different colors of light, uh, will the different colors of light cause these thermometers to rise up to different temperatures, and in fact they did. So this helped kind of get the idea across that different colors of light have different amounts of energy. Um, but what was really interesting about this was that they took uh, some of these thermometers and they pushed them beyond where any light was. So they took a couple of thermometers, they were measuring the different colors of light, and then they took the thermometer and they pushed it where there was no light, or at least no visible light. So they pushed it a little bit past where this red light was, and to their surprise, the thermometer actually was getting quite warm. And so they concluded there must be some invisible light, some light that we can't see. So they called it this invisible light. And since it was next to red, they called it infrared. So what we now called infrared or IR. So, but they said at the beginning they described it as invisible light, this new kind of light, because nobody up to this point had conceived that there could be any other form of light other than light that we could see. And pretty quickly, similarly, they discovered that there was also energy or light beyond the blue, beyond the purple, beyond the violet. So red, orange, yellow, green, blue, indigo, and violet is considered to be the bluest color that we can see. And when they put a thermometer past where that violet light was, where there was apparently nothing, at least nothing that we could detect with our eyes, that also was getting hot. And so they said there is some invisible light beyond violet, and they called that ultraviolet. And so there is light beyond what we can see. So we want to consider light to be not just the stuff that we can see, but beyond the stuff that we can see. Okay, so we're back here. So again, beyond the violet, so red, orange, yellow, green, blue, indigo, and violet, beyond violet, there is still light. We just can't see it. So this is called ultraviolet. And going the other way, beyond red, there is light. We just can't see it. And we call this infrared. So there is more light than we can see. And we call every form of light the electromagnetic spectrum. Okay? Now before, well, actually, okay, let's look at the electromagnetic spectrum. Boom. Okay, so so what was being described in the video, let me zoom in a little bit, make it a bit bigger for you guys, hopefully. That's not working. All right, anyway. And so as it turns out, there's the light that we can see. So that is some amount of the light that is out there. And then there's stuff that we can't see. So infrared, over here, infrared. So going on the red side, infrared. And then there's also microwaves. They're what we consider a form of light that we can't see. Radio waves are a form of light that we can't see. And on the other side of violet, there's ultraviolet that we also can't see, and X-rays that we can't see, and gamma rays that we can't see. So there's a whole bunch of stuff that we can't see. And what does this line mean, this squiggly line mean, and all that stuff? Well, this is what we call the wavelength of the wave. And I have a little simulation to help describe that. Okay, so this is just a simulation to describe wavelength. I just want to get this point across. And so what you'll see here, especially when they make a little pulse, is that the waves move outward at the same speed. So hopefully you saw that when they made a little pulse. So both of these characters are creating waves, but watch when they make a pulse. Note that they both travel across the same speed, the screen at the same speed. And so waves of a particular type are going to travel at a certain speed. So for example, water waves are going to travel at a certain speed. Sound waves are going to travel at a certain speed. And light waves are going to travel at a certain speed. And light waves, and all waves, as you'll notice here, when they move out, you'll notice they've got a little bit of a different shape between these two waves that are being generated. Both waves are moving outward at the same speed. One has a shorter wavelength. The one on the bottom has a shorter wavelength. The wavelength is basically, you could think of it as the distance between the peaks in the waves. And you can tell that the wave on the bottom has a shorter distance from peak to peak. The wave on the top has a longer distance from peak to peak. So we would say the wave on top has a longer wavelength, and the wave on the bottom has a shorter wavelength. Now, if both waves are moving outward from the source at the same speed, why does one wave have a longer wavelength and one has a shorter wavelength? Well, let's focus now on the motion of these two sources. The guy in the bottom is going to move up and down more quickly. We say he has a higher frequency. He's vibrating more quickly. The guy in the top is moving up and down more slowly. He is vibrating more slowly. And so the source that has a higher frequency of vibration creates a shorter wavelength. So if I wiggle up and down faster, I create a shorter wavelength. If I wiggle up and down more slowly, I create a longer wavelength. Okay, so the wavelength is really a reflection of how quickly the source is wiggling, how quickly the source is oscillating or moving back and forth. Okay? Okay, so we're back here again. So what this little representation is, it's saying that um, these types of waves, let's say radio waves, have a kind of a long wavelength. So relatively speaking, this is a long wave. Microwaves are created by sources that vibrate a little bit faster than radio waves, and so they're going to have a shorter wavelength. Infrared is going to have a still shorter wavelength. Visible light that we can see has a still shorter wavelength, and then ultraviolet is even shorter. X-rays are created by very fast vibrating sources, and so they are shorter waves still, and gamma rays are created by even faster vibrating sources, so they have even shorter wavelengths. Okay, so when we talk about these wavelengths, it's really all the same thing. All of these waves are created by you could think of it as electrons vibrating up and down. When we create radio waves, we make electrons go up and down in a piece of wire called an antenna, and that creates a electromagnetic wave or a light wave that moves outward from the radio antenna. And similarly, in a microwave, we have an oscillating source and we get an electromagnetic wave or a light wave that comes out of the microwave source and so forth. And it's just that the source, when we're moving stuff up and down in a radio antenna, it's moving up and down quickly, so the wavelength is not super long, but compared to other forms of electromagnetic radiation, the wavelength is long because the source is vibrating relatively slowly. So all of these waves are caused by electromagnetism. It's just that the source is vibrating at different frequencies. So all of these things that we think of as very different things, right? We think of visible light as something very, very different than microwaves, and we probably think of visible light as something that's very, very different than X-rays. But they're all light. They're all electromagnetic radiation. It's just different frequencies of light or different frequencies of electromagnetic radiation. All of these things, radio waves, visible light, X-rays, they all move through the air very, very fast at the speed of light, 300 million meters per second. So they move through the air very, very quickly, and they can move through outer space very, very quickly at the speed of light. Okay, so they're all the same thing. We just name them differently because we use them for in different ways. But all of this stuff is really light. Okay, so you want to start thinking of radio waves as light, microwaves as light, just light that we can't see, infrared radiation as light, visible light as light. These are all just forms of light or forms of electromagnetic radiation. We can see some of it, we can't see some of it. But many of these things are very useful to us, so we give them names because they're useful to us. So we give them names for what they're used for. Microwaves we use for cooking. Microwave light, you could think of it as this way. Microwave light we use for cooking. We can't see it, but it travels at the speed of light. Radio light travels at the speed of light, and we use it for radio communication and so forth. So I just wanted to get the point across that all of this stuff is electromagnetic radiation. Whether we can see it or not, it all travels at the speed of light, and they just have different wavelengths because of the different frequency of oscillation of the source. But all of these things are just forms of light. And so all of these things can travel through outer space, just like light can travel through outer space. And so we can detect radio waves coming off of stars. We can detect microwave radiation coming off of stars. We can detect infrared radiation coming off of stars. We can detect visible light coming off of stars and planets and objects and so forth. So when we're actually look out at the universe, we don't just look at the visible light. We look at all of the light. We build different types of detectors to look at. A lot of it looks at the visible light, but some of it looks at the infrared light or infrared radiation. Some of it looks at the microwave light. Some of it looks at the radio light. And we look at all these different frequencies of light, and it just gives us more and more information about the objects that are out there in the universe. Okay. The next thing that was discussed in the video is fundamental forces. Okay, so we said that there are 4 fundamental forces, right? Gravity, a weak force, an electromagnetic force, and a strong force. Okay, so there are 4 forces, and as described in the video, gravity is the weakest of, or is the least strong of the forces, let's put it that way, or I guess the weakest is a way to describe it. I hate to use the word weak because one of the other forces is called the weak force. And I just want to emphasize, what is a force? A force is just something that pulls objects together or pushes them apart. It's a force between objects. Okay, so we know gravity pulls objects together. Okay, electromagnetic force is basically a force between charged particles. So if you have 2 like charged particles, so 2 positively charged particles or 2 negatively charged particles, they will push each other away. If you have 2 oppositely charged particles, they will pull each other together. So that is the electrostatic force, which is part of the electromagnetic force. Okay. Most of what we experience in our lives has to do with the gravitational force and the electromagnetic force. And so we'll talk a little bit more about both of these forces because they're very important. They can explain really everything that pretty much everything that we experience in our lives. If you go down to enough detail, everything that you experience in life, you could explain by gravity and the electromagnetic force. Why you don't fall through a chair, how your cells function, how blood vessels function, how your brain works, how electrical signals are transmitted from your brain to your legs so that you can walk. Why planets are held together as balls of mass. Everything that you can think of, you could describe by gravity, even down to by gravity and the electromagnetic force, as well as these other forces. And so, if you really got down to a fine level, everything that you experience in life, you could explain by these 4 forces. Okay. And I'll send some videos out later that kind of highlights a little bit of that. It's difficult to explain everything that way, but in reality, everything comes down to these 4 forces. Now, the weak force really operates primarily at the very subatomic level, well inside the middle of an atom, as well as the strong force. And so, both of these forces they explain how atoms function, how atoms are held together, and things like that, but they don't really explain a lot about our daily interactions, about things that we experience in our daily lives. Whereas the electromagnetic force and the gravitational force really explain the experiences that we have every day. Okay, and let's just as I said, gravity is an attractive force. I just want to do a quick simulation of gravity. Okay, and I will send you this video, but this is just a simulation of gravity, and it is showing how this would be an example of if I've got, after the Big Bang, when the universe started, there was just little tiny particles out in the universe, and those tiny particles over long periods of time, because of gravity, began to clump together. And then those clumps of material began to form larger clumps of material. And some of those clumps of material became things like stars, and some of those things became planets. And this is a simulation that is just basically showing you how, and this would happen over a very long period of time, but how a planet could form. And what you're seeing is a bunch of these particles that were just out in space after the Big Bang, and things are beginning to clump together. And you can see gravity's pulling all these things together, but they don't always. Some particles just kind of fall directly in and slam into an object, but a lot of times the particle, even though it's getting pulled towards an object, and you can see that one object that's sort of becoming large in the middle there, that planet becoming, starting to form there, and you can see little particles are gravitationally being pulled in it, and that planet is getting a little bit bigger each time a couple of particles fall into it. And this is a process that takes millions of years, if not billions of years. It takes a very long time for all these little particles to kind of gravitationally be pulled together and form a planet. But you can see how that is happening. But you can also see a lot of these particles, even though they're being pulled toward the planet, they miss the planet, right? And they kind of form these they kind of miss the planet and kind of form little sort of elliptical or circular paths around the planet. And eventually, a lot of those objects, even though they kind of loop around the planet a few times, they do eventually kind of fall into the planet and just simply become part of the planet. But eventually, a very, very small number of those things will fall into a perfect orbit around the planet and will not fall into the planet. And those objects will kind of become objects that just orbit around the planet. And so you can see how over time, gravity causes these objects to pull into the planet and make it a bigger planet. But eventually, if this process kept going on for, and this is obviously a very sped up view of this process, this is a simulation, but and what's going on here would take millions and millions of years. But eventually, if you let this process go on for very, very long periods of time, the material kind of comes together primarily in a few balls with some small amount of stuff orbiting around it. And that's true of our solar system, right? Most of the objects in our solar system, most of the mass in our solar system, most of the mass in our solar system came together in the sun, and we've got some small things like the Earth and the planets are revolving around the sun. And that's all because of gravity. Okay, gravity explains how all of that takes place. And gravity is one of those four fundamental forces. Okay, so I just wanted to give that just kind of another talk about those two videos, light and the four fundamental forces. They're both very, very important things for astronomy, because everything we know about the universe, we know from the light that comes in, whether that's visible light or invisible light, in the form of, let's say, radio waves or microwaves and so forth. And these four fundamental forces, particularly gravity, pretty much everything, every shape that you see in the universe is primarily a result of gravitational force pulling objects together, and some of those objects end up simply being in orbit around a larger object. Okay, so that's it for this, and I will give you a form with some quiz questions and some reflection questions. All right, I hope you enjoyed that. Thanks. Bye.